Math 1343, hypothesis tests, population proportions. Testing one population proportion, the critical value approach, example 2. A government agency claims at least 20% of its citizens were obstructed from voting. In a sample of 500 citizens, 50 were obstructed from voting. Can we conclude at alpha equals 1% that less than 20% of citizens were obstructed from voting? Well, let's jump right into it. Step 1, state the hypotheses. H0 colon, HA colon. Let's start with a claim by the government. At least 20%. Context-wise, we don't need anything else. The fact that they said at least 20% means we're talking about proportions and saying that it is at least 20%. To be at least 20% means to be greater than or equal to 0.20. And again, that has to be our null hypothesis because this claim permits equality. It allows for the possibility that it's exactly 20%. So where's our alternative? It's actually embedded in the question. Can we conclude at alpha equals 1% that less than 20%? Less than 20%. There's our counterclaim. No, we say that proportion is less than 20%. And we have our hypotheses. Based on the alternative hypothesis, will this be a left tail, right tail, or two-tail test? Less than is left tail. Which takes us to step 2. Sketch the regions, determine the z-score separating them. These are your critical values. Bell curve. Left tail means we shade in the left tail. Giving us a rejection region on the left only. A non-rejection region in the middle, including the right tail, because if evidence lands over here, that's greater than the middle, that would be greater than 20%, which would agree with their claim. The area is the significance level, and so we know that the area of this tail is 1%, but as a decimal, 0.01, but as a 4-digit decimal, 0.0100. Find our critical value, z, using our z-chart. You'd think I would have these remembered because I've taught this so much. But I do have a z-chart pulled up for my convenience. And 1%, I'll recognize it the minute I see it, is going to be negative 2.33. I'm assuming, especially if you're taking my class, that at this point you're comfortable with the z-chart going forwards and backwards. So we have our critical value that separates rejection from non-rejection. Step 3, calculate the test statistic. I do want to remind you of the formulas. We are calculating z equals p hat minus p naught over standard error. Standard error is the square root of p naught times 1 minus p naught over n. So let's start by calculating our standard error. Remember, p naught means the hypothesized value of p, which in our null hypothesis was 20%. So our fraction starts with 20% times 1 minus that, which is 80%, over the sample size. We sampled 500 citizens. So let's see what our standard error is approximately. My advice is to calculate the inside of the square root first. 0.20 times 0.80 divided by 500 equals, and then square root that answer to 4 decimal places, 0.0179. Now, in order to calculate our test statistic, we need to calculate p hat first. P hat is the percent of the sample with this characteristic. it was 50 out of 500, that's 10%. And by the way, if the decimal didn't end, we would take it to 4 decimal places, round it to 4 decimal places. So our test statistic, the z-score we're going to compare to the critical value, is what we got from our sample, which was 10%, minus what we hypothesized in the null hypothesis, which was 20%, over the standard error, which we calculated as 0.0179. And let's see what that's equal to approximately. The difference is negative 10%, don't really need to do the subtraction. Divided by 0.0179, and to 4 decimal places, I get a test statistic of negative 5.5866. Let's put a box around that. Things get kind of congested around here. This is our test statistic. And step 3 is done. We've now converted our sample to something comparable to our critical value. Our 4th step is to decide whether or not to reject the null hypothesis. This test statistic is pretty large, negatively speaking. 0 in the middle, negative 5.5866 would be very far to the left of negative 2.33. But it really doesn't matter how far past it is. All that matters is it went past the critical value into the rejection region. And because our test statistic landed in the rejection region, our decision is to reject the null hypothesis. So mentally, what we're thinking is, null hypothesis, you have been rejected. Our evidence is strong enough to reject you and replace you with the alternative hypothesis. And now we can answer our question, which is step 5. Can we conclude at 1% that less than 20% of citizens were obstructed from voting? Again, the trick to answering the question is to ask yourself, which hypothesis is it asking us to conclude? Less than 20% was the alternative hypothesis. So this is asking, can we conclude HA? At the end, did we accept it or did we accept the null? We accepted the alternative hypothesis. So can we conclude that? The answer is yes. For my students, I will ask you to answer the question in the context of the problem. Saying yes is not contextual. It's just the beginning. Yes, we conclude less than 20% of citizens were obstructed from voting. Does that mean less than 20% of citizens were obstructed from voting? No. It simply means our evidence supports that. Does it mean at least 20% weren't obstructed from voting? No. Our evidence merely doesn't support that. All right, so testing one population proportion using the critical value approach is very straightforward and predictable. State the hypotheses. Alternative will help us to sketch the regions and determine the critical values that separate them, keeping in mind that the significance level represents the total area of the rejection regions. Step 3 is to just convert our sample into something comparable to the critical value so that we can make a decision in step 4, and then finally answer the question. One thing you'll notice as we go from one type of hypothesis test to another is that the flow is pretty much the same. We just have to change formulas and z's to t's when the time is right. But that time is not right yet.